Hi, my name's Melanie Warrick, and I am here to talk to you guys today about reinforcement learning. So I have been fortunate to be able to speak at a couple of PyCons in the past, and this is my first PyCon Russia, my first time in Russia, so thank you very much for having me, and this has been amazing. So reinforcement learning. The reason why I chose this topic is because it is a topic that falls into a space that I've been doing a lot of technical talks about. And to give you a little bit of an understanding of myself, I worked at change.org for a little while, working on putting machine learning in production. I worked at an open source neural net worked on an open source neural net framework that was in Java, that was not TensorFlow, for a couple of years, and then I joined Google. And in Google, I am doing developer relations, and I am doing a lot of talking around and about cloud and about AI. And I'm actually a co-host on a podcast. It's called the GCP Podcast, the Google Cloud Platform Podcast. So I've got a lot of stuff out there. But today is going to be about reinforcement learning. So reinforcement learning, it's pretty much what it sounds like. You're trying to drive, ultimately, some technology and influence it with a goal that has a reward attached to it. You're trying to influence behavior, and we're trying to do it with tech. So there's a goal. The goal is driven by a reward. Now, how many of you know about reinforcement learning? Hey, okay, all right. Well, this is going to be a refresher, but I can see that the majority of you don't, and so this will be a little bit of an overview. And what I'm going to do right now is I'm going to give you an understanding a little bit about how it's applied, as well as then dive into the components and some of the core mathematical structures. How many of you like math? Hey, wow, more people than I expected. I don't know, maybe that's like 20, 30% of the audience. It's probably more like 20%, but still. Yeah, we'll try not to go too much into the math, but I do have some equations for you guys. Okay, so reinforcement learning, it's about goals and rewards, or it's about rewards. That's what you want to get. You want to get the most reward. Now, I want to level set real quick on terminology. Artificial intelligence gets thrown around a lot. Everybody's talking about it. It seems to be labeled on everything. So let's just be clear. Artificial intelligence is about the science and technology of making intelligent machines. Yeah, that's easy. You know what that is. You can pinpoint it. You can be like, that is AI. It is labeled on everything nowadays, and that's just how it is. It's becoming like internet or air. But it is, the idea behind it was that originally people were thinking this is going to make human-like machines, and they were waiting for that kind of experience. And we don't really have general AI. That's what's AGI. And people are working on that. But artificial intelligence is encapsulating this idea of making intelligent machines. And part of making that are using tools like machine learning. And so machine learning are a set of algorithms that you use to have the machine be able to abstract a problem and solve a problem in interesting ways. I'm going to just leave it at that, but there's a lot of machine learning algorithms out there, and one of them being neural nets. And usually when you hear deep learning, people are talking about neural nets. Technicality, not all neural nets are deep, but you don't have to worry about that. When we talk about deep learning, we're talking about neural nets. Now, there are those who would say that this is exactly correct, but whatever, I threw it in there. Reinforcement learning, kind of machine learning. Some would say it's not machine learning, it's its own thing. It's an approach, it's another approach, it's another set of models to help the machine abstract a problem. And it uses neural nets, so that's why I've got a little bit of a connection going on there. And these are all tools that you can use to try to work towards AI. They're not the only tools out there, they're not the only fields, and you can combine them all in different ways. So that's my little bent on terminology. Let's talk a little more about how you see reinforcement learning in the world. Now, when we talk about it, usually you hear it in relation to games, which doesn't give it a lot of weight when you think about it. Games seems a little flighty. It's like, hey, or not flighty, that's not fair, but it seems it's fun. Games are fun. Who doesn't like playing games? Or maybe there are people, but most of the time you enjoy it. But it doesn't give it a level of weight, I think, unfortunately, the weight that it deserves, the respect that it deserves. Now, the way we've seen reinforcement learning, back in like 1992, Gerald Tesaro, and I'm probably botching the name, but he developed this game that was in essence It learned how to play backgammon. And it learned how to play backgammon in new and inventive ways because he gave the game this approach to play it with reinforcement learning where he didn't tell it how to play. He said, I'll give you all the parameters on how the game, the structure of the game, the actions, the way you can move throughout. I'm going to let you figure it out. And what was interesting in this application was that it identified new ways to play the game that a human hadn't thought of. It came up with innovative ways to play it. Cut to a couple of years ago, AlphaGo. I think everybody's heard about this at this point. But DeepMind had developed AlphaGo, and this played against Lee Sedol and won, which was one of the top champions in the space. And again, what was most interesting about this was that it played the game in innovative ways. It did plays that a human hadn't thought of before. And now these types of games are being used by humans to be able to learn new ways to play the game themselves. So games are fun and fascinating, and the reality is they're contained spaces to be able to experiment with. They're valuable because you know what you're trying to get out of it, and you know how to solve that problem. It's contained for you. It's so much harder to experiment with this in real life settings. But once you know it's doable, once you know that you see it working in a game like this, then you know you can start to apply it to the real world. One other note, and actually I'll come back to that. So let me just break it down for you in this regard. We have seen reinforcement learning applied to real world problems. Now, it's still limited in terms of how it's being applied, but a couple of years back, Google, for example, we went and we said, okay, we're going to apply these types of algorithms to solving or to improving how we use our energy in our data centers. We were able to reduce our cooling energy use by 40% across all the data centers. We had a lot of data centers out there, and they're spread out across the world. And these data centers are in environments that are all very different, and we use sensors, many sensors, you talk about your IoT devices, in these different data centers to collect information about the air quality, the humidity, the temperature, all of that. And we were able to use reinforcement learning approaches to be able to reduce cooling energy use. More recently, DeepMind's definitely the expert in the space. They published a paper about how they were using reinforcement learning to teach an agent a technology, or their computer, I don't know, agent is the term we use for the tech as it explores reinforcement learning algorithms, and I'll show you that in a little bit more detail in a minute. But they taught an agent how to navigate in cities with just images that they'd captured from the Street View data set. And they used reinforcement learning to accomplish that. And not only could it navigate like in parts of Manhattan, then they were able to transfer that agent to other cities like London and Paris and feed it images of the streets in London and Paris, and that agent was able to quickly learn how to move through the streets, kind of on a scavenger hunt, moving from I've started at this point and I got to find my way to whatever destination you're trying to get to, or maybe a taxi cab. So these are ways to think about reinforcement learning potentially solving real-world problems, that it is doing real-world problem solving, and you can start to think about it applying it to any situation in which you can say, I've got a goal, I can give it a reward, and I want to try to optimize for that reward. Now, the thing I want to highlight, and games are a really great way to explain this, is that, you think about the game of tic-tac-toe, the state space for this, the number of options. When you play whatever X or O, and your opponent will then take his turn or her turn. You can map that out into almost a tree structure. And with tic-tac-toe, you can fully map that tree structure. But with other games, as they get more and more complex, you cannot fully map that tree structure out. That's why techniques like reinforcement learning are important, because we do not have the full memory capability or the compute power to map out the size of some of these state spaces. And this is just with games. So with Go, for example, we couldn't fully map it out, or even if we could, we wouldn't be able to traverse the tree fast enough to respond in the time you have to respond in a game. Now imagine taking that and stepping that up to a level of like a self-driving car. You're not going to be able to fully map out the full state space of all the things that could happen, and then also traverse that fast enough for the car to make a decision and change whatever it's doing. So this is very important, and I'm going to get to this a little bit more as I break into what is and how do you think about reinforcement learning in detail. So let's talk through that. When you're doing reinforcement learning, there are core components. The core components exist of your agent, which is your technology, and you're going to be teaching that agent certain things. The agent will exist in a certain state, like currently the state that I exist in is I'm standing on the stage. That's my state. If I walk down these stairs, I would take that action, and I would then be standing down there on the floor. So if this mouse would be at the starting state of the maze, and when it turns right, it's now in a new state in the maze. And the maze is the environment in which it acts. The reward, of course, being that cheese, and it's got to get to that reward. It wants to find that reward. And it has certain actions it can take. And then time. Time is not listed up here, but that is also a component. Typically, you want to get that mouse to find the reward as quickly as possible. Now, to dive a little bit further into this, imagine your agent is this little newborn babe. It's like new in the world, and it knows nothing, and it's got to figure itself out. And the main thing you have control over is its behaviors, also known as the policies. It's exploring the space. It's got its environment. The environment is typically referred to whenever you look at anything related to reinforcement learning. It talks about it as an MDP, or the Markov decision process. The Markov decision process is ultimately saying that, hey, my current state is all I need to know to be able to determine the next state that I'm going to move into and that action I'm going to take. That's all I need. Most environments in reinforcement learning are typically going to be MDPs, but not all environments. And usually in your environment, you'll have components like your transition function and your reward. Sometimes you'll know nothing about your environment. Sometimes you're literally, I'm starting from scratch and I'm going to spend a lot of time trying to figure it out. This is a large part behind why it takes so much time to learn anything and get anything useful out of reinforcement learning, because you have such little, your technology has such little knowledge about what it's exploring. So your environment could be continuous, could be discrete, could be continuous, could be partially observed. There's a number of variations that you have to consider in terms of what specific environment is your agent exploring. The transition functions themselves are specifically helping to define some of the limitations within the environment itself. So like if you're trying to get from point A to point B, and it's point A from the first floor to the 20th floor and the elevator's out, then that's going to change the transition function in terms of the percentage probability of you moving from A to Z to a much lower percentage. And it's all dependent on the environment. So you define in the environment certain limitations, certain transition functions to get from states to states, and based on the way the environment is set up. And the reward, of course, you define what the reward looks like. Now, the states and actions, these are the states in which your agent exists and the actions that they can take. And as I mentioned earlier on with the example of the games, you can do a tree. You can do a tree of what those state and actions look like. And that tree will say, I am the dragon standing at the bottom of the citadel, and I decide to fly as my action, and now I'm flying above it, and I see a party. And that's like, hey, there's a party. Now what am I going to do? So you have your state search tree in the way in which you explore this environment. And you're always looking to get to your reward and do the most optimal policy, your optimal behavior to get to that reward. Whenever you look at any kind of mathematical equations in relation to reinforcement learning, you will typically see a star and a pi in relation to optimal policy. That's what those are usually referring to. If you ever see star in front of something in equations in reinforcement learning, they're always going for optimal, 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 optimal. So to actually design the reinforcement learning algorithms, there's a couple of different approaches, and I'm going to step you through those. Model, couldn't be any clearer. In this case of model, we're talking about the environment model. This is how you track and capture information about your environment. So that's what we mean when we say, and you see them reference model. Couldn't be more confusing, considering we also like to talk about models of, how we model the actual behaviors or different things like that. I'm going to try as much as I can to distinguish between the two for you. Value function. Value function is when you say, okay, I've got a reward. At the end of this game, I have a reward. But now I want to try to take that reward and sort of parse it backwards and apply some variation or fraction of that reward on every state or every state in action. In policy is about trying to give a model of my behaviors, to try to provide, like, if I'm in a maze, I should turn right every time. That should be my policy. That's going to be the thing I can control as an agent. This is now the behavior I think is the best behavior to have. So for the environment model, you know, if you're trying to track something that is massive, that's too big to fully model, you might at least try to capture some elements of it. And you can take all types of forms in order to store it. Table form is one of your simpler options out there. You know, there's other options like neural nets. Actually, if you don't know about neural nets, and I know I've already mentioned them a few times, I have some great content out there that explains them in more detail, and I'd say, you know, check it out. But ultimately, it's a mathematical structure that's helping you abstract information. So if you track information about your environment, what it really means at the end of the day is it's easier for you to make better decisions and have better behaviors, because you have a sense of, like, I've been to this space before, so I already know about this spot that I've been standing in, and I know that, you know, I know all the information I need to know about this spot, and I don't need to go back to that spot anymore. So, like, if I got stuck in a spot in the maze that I turned down before and I realize it's a dead end, then I won't keep revisiting that dead end because I've tracked that information. That's helpful, but sometimes there's like back doors and cheats well, cheats isn't necessarily a fair way to say it, but there's shortcuts. Shortcuts is a good one. There's shortcuts that you might miss, especially like in games. You know, there's those fun little shortcuts in some of the games out there. You might miss those if you don't keep exploring. So you want to be careful about getting a map and thinking that this is telling you everything you know. So the beauty of going model-free is it gives you more opportunity to explore and see some opportunities that you may have missed by assuming you already knew everything about the space. The hard part about not tracking your environment is that it is much slower to train, typically. Now, the way this can look, and whenever you're doing a model of your environment, they refer to it as planning and learning. But the way this will work in general, when you're going through and trying to build out your reinforcement learning algorithm, is, you know, you have your agent, you got your little baby dragon, and it's like, hey, I'm new, I'm going to try some things randomly. Maybe it has a little information and it's trying some things and it's trying not to kill itself. But it gets some experience, and it could directly update the value function or its policy, or it's going to learn from that and apply it to however it's storing information about the environment, and then it's going to plan. It's going to make some plans on and potentially apply those plans to the value function and the policy. Okay, I will come back to that, because let's talk a little bit about the value function. So the value function. As I mentioned, this is an approach to reinforcement learning that says, hey, I need to get a reward, and then I want to try to abstract that reward or take that reward and bring it back and apply it across the board in terms of all the states I was in prior to finally getting to that reward. When you work in this space, a hello world of reinforcement learning could be the grid world. You'll typically see this. It's small. It's nice and easy. It's only got, you know, 12 different cells. But technically, one of them you can't really go into because it's a wall. And one of them is going to give you a reward, and one of them is going to give you a regret. You're going to let your agent loose in this. You can let it loose for several hundred times, letting it explore the full space. It's going to fully exhaust every single spot. And you want it to get to the point where it just stumbles around in here until it hits a reward or hits a regret. And you track that information. And you can think about it stumbling around in here so many times. And you track this information, and it's almost like a frequency. How many times was it in a certain cell, and then it finally got to the reward? How many times did it visit certain cells that finally led to a reward? You will feed into your program information about, you know, what you know about the environment, what you know in terms of the states that it's currently in, and what you know in terms of the actions that it can take, and its transition model. And then you will do this algorithmic approach that's typically known as prediction and control. So the prediction part is where you are going to evaluate any policies you have. And typically your policies are going to be something that is possibly random at first. And you'll update your value. And there may be no value at the beginning, or they may be very minimal value or equal value across the board in all the states that you could be in. And you'll explore. You'll just, like I said, you'll go through and you'll explore that grid world over and over and over and over again. You'll keep track of the information. And then you'll come back with your control algorithm, and you'll start to say, okay, I want to focus in on specifically where I'm getting the most value, where I'm seeing the most return in terms of reward. The Bellman equation, yeah, I got an equation for you. The Bellman equation is the common one that people start with when they talk about reinforcement learning and they use a value function. This is applied as your predictor. This is ultimately saying, hey, do I have a reward in this 0-0 spot that I'm standing in? No? Okay. Do I have a discounted reward? And that discounted reward is based on, I've been in this spot before when I've done a string of steps, and I got to a reward eventually, and I've taken a fraction of that reward and applied it to this spot. And then the control section is going to be something like greedy. Now, there's a number of other approaches you can take to this, but greedy is your like first go-to. You know, it's like, what gave me the most return? What do I want to exploit? And so you do this again and again and again, and you eventually start to get some values for that grid world spots. And you start to see, hey, in 0-0, you know, I have a certain value, and I can see if I go to 1-0 that my value is much higher than if I go down to 0-1. So I'm going to go over to 1-0 because that's a higher value in terms of that state. Okay, so value functions. I'm going to just simplify a few things here, and then we'll go into policy. But for value functions, they range roughly into these, or they fall into these main key categories. One, are you going to fully define your environment? And two, how far do you have to go through the environment to the reward before you'll start to update and make updates to your policy? So the exhaustive search, tic-tac-toe, you can fully exhaust the whole thing. Dynamic programming, you're still fully exploring, like you'd explore the grid world, but you might make updates to those policies as you're going. It's more like online policy. So you're updating it before you've fully gotten to the reward, or you've ended at the end point. Monte Carlo is accepting the fact that the environment especially may be too massive for you to explore fully. Go is a great example where they use Monte Carlo. So you'll do a lot of sampling. And we're talking a ton of sampling, a ton of just exploring the tree until you get to a result. But you don't fully map out the tree. You only do sampling until you get to the end. And you're required to have episodic to be able to get a result and feed it back. And TD learning will combine both dynamic programming and Monte Carlo. TD learning is doing the, I'm now exploring, but I'm also sampling. So I'm not going to fully map everything, but I am going to update as I explore. I'm not going to wait till the end. Now, I gave you, because I know you all really wanted this, but I had this up here in terms of, for dynamic programming and for Monte Carlo, some of the equations. The one thing I'm going to take a minute and reference for you is that I've been talking about value functions in relation to giving values to these states. If you've ever heard of Q learning or Q values, they're referring to giving values to the states and actions as pairs. So this is where Q comes from. But yeah, I've talked to you a little bit about the dynamic programming, about Monte Carlo sampling, and I've talked to you about temporal difference learning. So Deep Q network, DQN, this is what DeepMind used when they were doing the Atari experimentation that they did several years ago. DQN is what they came up with. This is a temporal difference learning algorithmic approach, and it is using, of course, Q values. So, and it's combining it with neural nets. Oh, neural nets. Got to get some neural nets in there because neural nets solve everything. So in this case, you're passing in state and actions, and you're putting it into the network, and you're getting a Q value out, or you're just passing in a state as the input, and the output is a Q value per action. So it's kind of the same, but not exactly. There are various techniques that you will apply. I've got up here listed like target network and experience replay. I'll let you look into that if you want to dive into this further, but these are techniques they use for DQN to help it converge, to help it actually come out with some type of result. When they did this, let's see, can I play it? No, I cannot. Oh, that's a bummer. Oh, wait. Nope, can't. Okay, I was thinking, wasn't sure in this system if I was going to get to play it, and it's a bummer that I can't. But as I mentioned, DQN was used to help the Atari games initially when they were playing with these Atari games and helping them learn. What you don't get to see is that the Space Invaders, for example, you know, in the beginning, like you watch, especially when you watch any of these Atari videos, and there's a bunch of them on YouTube. You can watch them if you haven't seen them already, but you can see how the agent will start off early on where it's just like randomly moving around, but with time, it starts to get really good at just doing what it needs to do. And in this case, this little, you know, the little agent at the bottom figures out how to hide and avoid when it sees that the pixels are coming after it from the aliens above, and then how to quickly get out there and start shooting at those aliens. So, and it's really good with reactive games in particular. But if you're doing some type of treasure hunt, it's not as effective. So I think well, anyway, I'll come back to that one. So that's value function. Other one that I want to take you through in terms of the approaches in which you can try to solve reinforcement learning is policy. Now, what I mean by policy is you want to model the agent behavior. As I mentioned, like if you're in a maze, maybe your best practice is always to turn right, and that's going to be your policy until you've proven differently. If you're playing the game Rochambeau, for example, you can't come up with a value function for Rochambeau. There's not a higher value for certain action. You're only going to take one action, and they're all equally weighted. So at the end of the day, a uniform random policy is your best bet to play that game. So that's an example of why you would want to have a policy algorithm. They usually fall into, in terms of these algorithms, they fall into two main buckets. There's gradient and gradient free. And so with gradient, you know, it's taking a function and being able to map it. It's like usually whenever you look at anything with gradients, you look at it and it looks like a bunch of hills and you're trying to find the lowest point in the hills. You're optimizing the function. While gradient free, and that's where neural nets falls into. Gradient free, it's almost like a frequency thing to a degree. Evolution, was recently talking to somebody about how they were using it for improving systems performance, actually, with using various evolution and genetic algorithms. So an example that I like to mention, and this also brings up more Atari, because who doesn't love Atari games? Or at least maybe who didn't love Atari games? I loved Atari games. Policy networks, policy neural nets in particular, and policy search. Karpathy, who's a well-known researcher in this space, and it's now at Tesla, he wrote some great content that's out there online if you haven't seen it before. But in particular, he put out a blog about reinforcement learning that stepped you through how to run a Pong game. And there's some great There's some great Python code that you can check out that he's got out there on a GitHub repo. And ultimately what it's doing is it's taking in the frame data and it's converting it into a byte array of about 100,000. It's defined the environment. It's these two paddles, and one is run by of course, the game itself, and one is run by the agent that you're training. And the actions that the paddle that you control can take is up and down, or staying in the same spot. And then the reward, of course, is you get +1 if you get past your opponent, -1 if they get past you. So what's interesting is when it starts to play, you know, the paddle is just jiggling, it's not even figuring out where to go. But with time, and I ran this on my own, it ran for like a couple of days where I think the first day it did nothing, like it wasn't winning at all. But by the second day it was starting to win, and then by the third day it was winning all the time. And it's finding the most optimal way to play. Now if you know anything about this game, you'll know that the way the computer's built is that it's keeping its paddle always in front of the ball. So there's a technique to getting past that. Since this is PyCon, I wanted to show you some code, and I know it's a little dense, but I'm going to step you through TensorFlow. Now, how many of you have heard of TensorFlow? Hey, okay, interesting. So TensorFlow is our open source neural net platform that's based in Python. And neural nets, again, if you haven't spent a lot of time with neural nets or don't know a lot about them, it's an algorithm. It helps you abstract a problem. It helps solve for making predictions and classifications for certain types of problems. It's very popular with images and with language in particular. With TensorFlow, I'm going to just step you through some core components that are playing out right now. This first page is really showing you how to set it up. This is the setup. This is saying, okay, this is how I'm going to build out whatever I'm going to run. Now, the first top 3 lines are really kind of creating containers that you're going to store information in. The top one is your observations. And in particular, what the observations are, it's subtracting one frame from another frame. So it's basically what was the frame, the previous frame, from my current frame, and I'm subtracting those from each other. And that is my observation. That's helping me see movement. It's helping me see the change, specifically where each paddle is and where the ball is. The actions, those are what I'm going to do. That's actually like, what did I do? Did I move the paddle up? Did I move it down? Did I keep it in the same spot? And the rewards are the results. And that's where you will store that information. Y model is defining the neural net. And when you build out a neural net, you talk about it in terms of layers. In this case, it's just using 2 layers, that's it. 2 dense layers. And if you know, they have a linear and a nonlinear transformation. And the nonlinear transformation is the ReLU nonlinear transformation, which is pretty common, as well as the softmax. The sample op. Sample op is basically the operations function that will sample what action to take. It will use the current state of the model, and it will sample out, should I go up, should I go down, based on my observation. The loss is the way you calculate what the error looks like from your neural net based on the reward, and your optimizer is telling you how to update that neural net based on the loss. And your training operations is in essence telling you minimize the loss. So you've defined the containers to hold the results and hold what was your input, what was your output, what was your action. You've created the model structure, and you've defined how to evaluate that model structure and how to then iterate and improve on that model structure. And that is what you've done here. It's really just laid the groundwork. The next slide is I'm going to just step you through a component of the actual code. And I also want to take a second and mention, so this code is something that my colleagues had put together, Martin, Yuhan, and Niraj. And I've got a link. Unfortunately, I don't think the people over on this side can see it, but I have a link to the code base in which they built this on, which is on GitHub. I have a link to also, that link also contains a great video that goes in more depth, as well as some slides that they have out there. And I will post this out later, so for those who are interested and want to explore this in more detail. So this second page, this second slide, this is really taking you through the process in which you can play the game, these key components of playing the game and training your model. Because whenever you're doing anything with neural nets, you're training the model and you're iterating on it to improve it and to get it to actually give you some type of result that's interesting. So that middle loop there in particular, that one that's the most indented, it says while not done, that's playing a full game. That's saying, all right, we're going to play to 21, and once somebody gets to 21, they've won. And while I'm playing, I'm going to track whatever my current frame is. I'm going to subtract it from the previous frame, and I'm going to then pick a random action based on my current model. And once I've picked a random action, and usually when you're just starting out, you're random sampling it. But as your model improves, it will start to increase probabilities based on the difference, that observation difference, to say, I think you should move up when I see this difference in particular. And it's really saying, hey, the ball started to move in this direction. I think you should move up. I think you should move down. So the action will give you that random sample of like, hey, this is the action I should take, and it then plays it. That pawn sim run is the way you play the actual game. So you've got this little inner generator, so to speak, that is playing the game for you. And it comes back with the game state, it comes back with the reward, and it tells you if you're done. Has somebody reached 21 yet? And then from there, you store your observation, you store your action, you store the reward, and you keep going until you've got 21. Now, the loop that is right above that, where it says while length observation is less than batch size, you will play this 20,000 times. So it's a lot of times. This is an example of why reinforcement learning takes a while, because the agent has to spend a lot of time experimenting and learning and trying things. And then once you, and when it's doing that and it plays each game, it's actually normalizing, well, it's doing two things here. If you'll see in these lower, I really wish I had a pointer. Does this point? Oh my God, it points. And now I learn. It's like almost done, and now it points. This is when I wish I had my computer in some ways. Okay. So here, this process rewards, discounting rewards. So that is helping you discount the reward. You know, I was talking before about the calculation of the Bellman equation. I'm sure you all remember that really well. Basically, you know, if you have a reward, and if you're not getting a reward specifically for a certain state that you're in, then you want to find out, did you have any reward, at what point did you have a reward, and you want to discount it back to the state that you were in the stream of states that you got to the final reward. You're discounting the reward, then you're normalizing the reward. And the reason why you're normalizing it is because out of those 20,000 examples, you're going to have a small number that got to an actual, some kind of value. And so you want to help boost the signal on that small number. So that's what the normalize does. Okay, so you run this 20,000 times, or you run 20,000 games, and you store everything. And you store it all, and then you go and you work with your training operation to update your model. And you'll do it all over again. So you'll experiment for multiple times. You'll feed that back into your actual model, and you'll let your model improve how it's performing. You'll let your model improve on the loss and minimize the loss. And that is the component, the key component for being able to run the Pong game. And they were able to do this, and I think it took them like a day or less than a day for it to get to the point where their Pong was able to win. And how did it win? And it won all the time. It found the best performance behavior was to move quickly, and I'm sure you've all played this before and you've seen it yourself, but the beauty of it is the agent could do it almost every time, to move the paddle very quickly as the ball got close, and to hit it on the edge so that it could send it at a vector that was fast and past what the actual other player was expecting. And that was the way it started to win. That was one of the best performing behaviors that it found to keep going after. That was its optimal policy. Okay, so one other thing I'm going to mention about these functions. And this is a common thing within reinforcement learning. We like to combine things. So in this case, we love to combine things all the time. And in this case, why not combine value function with policy? You may have heard of something like A3C. And if you haven't, now you have. It's known as asynchronous advantage actor critic. And what that does is it's saying, okay, we're going to use the value function, which is your temporal difference, as our critic to get a value. And we're going to combine that with a policy gradient, which is probably like a neural net, to update what our policy should look like. So we're going to track both, and we're going to optimize. And why that's useful, and I can't play this, but is it makes you able to explore your space faster. It's storing information that ultimately reduces the turnaround time to get results. It's interesting, this is a maze, and they were able to find that this maze, the search in the maze was much faster using those combinations versus using something separately. So you can track your environment, you can track the value function of every state or state in action, you can track you can put together some model for your policy, the optimal policy for your agent. You can combine value function with policy search. And you're looking at, hey, I've got my agent who is taking an action, getting experience. I can update my value function, update my policy. I could also learn from that and store it as in my environment model, plan and update the value policy. I can combine them all, I can combine parts of it, can try all kinds of different things. And that's how they do reinforcement learning. So a couple of the challenges that they have is in convergence, getting the model to actually have any kind of signal that shows that it's useful. And when I say model, I am talking about the algorithmic model that you're building for your reinforcement learning algorithm. The fact that, you know, like you look at a treasure hunt, for example, you have a delayed reward. So it's hard to see, it's hard to find that you'll get any type of reward. That's very difficult, and there's all kinds of techniques that they're working on to account for that. In the control section that I showed you before, you know, I mentioned greedy as being one approach. The reality is you want to give your model the opportunity to do more exploration. So it's this constant argument and trade-off of like exploration and exploitation. and how to generalize. Can I take something I've learned with one tool and apply it to another? Can I do what DeepMind did, where they said, hey, we've got our agent, it's learned how to navigate the streets of New York, and we can swap out one component of the algorithm we built and plug in a new one, and we can now have it learn more quickly on how to navigate through London or through Paris. So how easy is it to generalize? This is a tough one, and people are still working through that. And data, oh, it's always hard to get data. It's great when you're playing a game. You can have like the two, agents play against each other and potentially generate some interesting things. But still, getting the data you need to be able to run these types of algorithms, it can be very difficult at times. If you want to spend some time on it, some of the main libraries that are out there, these are not the only ones, are, of course, out of DeepMind, OpenAI, and Facebook. So those are ones you might want to look into, and I see someone taking a photo, so I'll give a second. And the main thing I want to mention, a couple of things I want to mention here. I've already talked about the exploitation. That's an interesting area if you want to spend some time exploring it, or transfer learning, be able to take a model, move it from one problem to another. Breaking down the problem is crucial when you're doing reinforcement learning. You take a goal and you need to then break it into steps. And optimal policy is always what you're driving after. I have some resources, some additional resources that you can explore that are interesting for reinforcement learning. And I have a bunch of images that I use. Actually, I'll take a second on the resources if anybody is trying to capture that. And no, I will also send this out. And then there are some folks and different groups that I worked with to help pull this together. The thing I'm going to mention at the end, and I don't have a video of this because I didn't think I'd get a chance to play it, but have any of you heard of RoboCup? I hear some, yeah, sure. Okay, all right, I am going to say football because I know that that's what everybody understands, and I'm not referring to my country's football. I am referring to yours. So RoboCup, it's fascinating. It's a bunch of robots. It's this game that has been run out of Japan since like the 90s for researchers in robotics to come together and play football with robots. And there's great videos out there if you haven't seen them on YouTube of the stuff from back in the 90s even to today. Some of the robots are creepy, some of them are really cute. It's a mixture, and it can be boring, it can be fun, it just depends on what soundtrack you're listening to when you watch them. But they are interesting because the goal they have is to actually have these robots eventually play, or many of them, want to get to the goal of these robots playing humans. And I know, you watch them and you're like, oh no, that's not happening. This is, never. Or maybe almost never. But, I mean, you think about Go, you think about chess. These were games people didn't think we'd be playing. Right now, OpenAI and DeepMind are both working on like StarCraft and Dota 2 in terms of games. These are much more complex multiplayer games to play, and it's only a matter of time before they get beaten. Will robotics be able to win at football? Will they be playing in the World Cup? Maybe they won't be because of regulations, but I wouldn't be surprised to see that at some point. And maybe that's not in my lifetime, I don't know. But I do know that these types of algorithms are what's making it possible for us to be able to solve certain problems like this. And it's not to be creepy or weird. It's more to say, I'm trying to say from the standpoint of, the impossible is why these things get overhyped. This is hard. Reinforcement learning is hard. It is hard to get these to solve these types of problems. But it's not impossible. And it's solving problems in interesting ways and coming up with innovations that you are not fully able to think of yourself yet. But it's great, and it's helping us in ways we don't know. And sure, when it plays football, that's exciting. But the real question is, how will it help us in more applied ways, like solving our energy issues? Maybe helping save people's lives. We don't know what that's going to look like yet, but that's where some of these algorithms can really play a role. And I cannot stress this enough. I am doing this is why it's exciting. I also recognize it gets overhyped. And so I don't want you to think it's easy and it's going to be solved tomorrow. And I don't think you think that. I mean, that was one thing I want you to be able to understand with, hey, this is not easy, but it's also not impossible. That's what I want you to understand. And I also want you to, if you want to explore it, go out there and explore it. And that's all I have for you guys. Thank you so much for having me.
I think we have a time for some questions.
Questions?
Hi, thank you for your talk. I wanted to ask, are there any techniques to predict the reinforcement learning machine time? I mean, there may be tasks that will take too long to make them profitable with reinforcement learning.
So you want to know if there's a way to predict the time?
Yeah.
Oh man, sure. Really easy. I have a watch in my bag. It does it every time. With all of these types of all these techniques, there's always the thing you hear everybody say, and I hate to say it, it's like it depends. But no, there's not a way to predict the time. You know, I think as some of these problems start getting solved, and you find standardized approaches, you're starting to get a better sense of what the timing, or I know you start to get a better sense of timing. Yes, but we don't have a tool right now or specific, here's some standardized timings for, you know, reducing energy cooling costs. I mean, that's not out there right now. I think it's only a matter of time before it does.
Thank you.
Other questions?
Hi, thanks for the talk. You mentioned that companies explore AI in games, and you mentioned Dota specifically. And there's a bot from OpenAI that plays 1v1, and they told us that they're going to make a 5v5 version this year. So it clearly takes some teamwork for those 5 bots to play. And my question is this, do you think that they communicate strategy between agents in the environment, or are they taught in such a way that they know how to help others and expect others to help them?
I don't know too much about how those bots are being run. I wouldn't be surprised if they do have some way of sharing knowledge between them. But in terms of specifically how that knowledge is shared, you know, it depends on how the model is built and the way the data is being fed between the models. Yeah. That's as much as I know about it.
Thank you.
Other questions?
Thank you for the talk. I want to ask, does Google have any frameworks for data scientists? For example, like Uber from Michelangelo, or Michelangelo from Uber. Do you know that framework? And etc. things to help develop models.
To help develop models, so I mean, TensorFlow is one way to develop models, and we have a number of tools that, in the cloud in particular, that are supportive of creating models. And DeepMind in particular uses TensorFlow on a regular basis. So that's there. I always love to refer to Kaggle as a source for great inspiration for just, you know, even if you're just getting started with certain problems, but they also work on real world problems, and they've got, I think I have a link for this. Let's see if I do. They have a link that they put out not too long ago. It is kind of small. Oh wait, no, these are my images. I don't see it in here. So they have a link that they put out not long ago that is listing, like out of all their competitions, many of the winners of those competitions, so you can explore some of those frameworks and you can see what types of problems they were solving. And that's a great way to get, you know, if you have a certain problem that you're solving and you can find something similar, you can get some ideas for frameworks. Yeah, and there's also, there's usually, and I know with TensorFlow we have, oh, I'm going to forget, I think it's TensorFlow Hub, where you've got frameworks that are recommended for certain types of problems and like specific neural net frameworks in particular.
Okay, thank you.
Sure.
Thank you, Melanie.
Thank you. Thank you.